Hello, calculus student. This video is for chapter 2.7, Integral of Exponential and Log Functions. You might say, oh, Miss Chan, we have already learned integral of exponential function using the exponential formula because we know, at least we know some formula of finding derivative and integral of a log function. Should be this one. Yeah, because we know d dx of e of x is e of x, right? Because e is an exponential constant, and if we use it to base, the good thing is d dx is e of x. And then if I do integral of e of x, it is e of x. The other things we also know is d dx of ln x, the log, which is the inverse of e of x, is 1 over x. And so if I do integral of 1 over x is actually, dx, is actually ln absolute of x plus c. Oh, I forgot plus c. Right, so these are the basic integral and or antiderivative, I would say, of exponential and log function that we know. But we'll look at the exponential and log function in more detail. And we actually, the goal is to use log to do more difficult derivative differentiation, which we will use in chapter 3 when we do integration technique. Other things that we want to know. So this is the objective. The objective is redefine log or the natural log function as not as the inverse of e of x, but actually as an area function. And then define our e. In the past, we have defined e as 1 plus, okay, so which actually we would know. E is 1 plus 1 over n to the power n when n is really, well, actually it's a limit. When n is really, really big. When we add a little bit of stuff, but then we do a lot of integral, then we say that is e, and we use this number. Okay, write it nicer. E is limit n approaches infinity, or x. You can use x 1 over n to the power n. That means you add 1 over 10 million, and then exponential it 10 million times that it approach a number e. You use it as a base and then define a function of exponential base like that. But we can also use define e as an area under 1 over x. And then it turns out that if we define log function this way and exponential function that way, it's exactly the same as we have defined. We'll further look at other derivative and integral of other base, and also use log differentiation to find complex derivative. Okay, so that's the goal for this. Because in some calculus class they have covered this, so I won't spend too much time on this. You can watch the videos. Basically, I like you to know log differentiation, how to use it. I like you to know how to use log to do complex derivative. Like I will mention it when I get into that example. Okay, so in the first video, we'll do some log properties review. This is very important for calculus. For any log base, we say log base b, m times n. Anything multiplied inside a log, you can split it as two individual log base bm plus log base bn. And if the two expression inside log is m over n, you can rewrite it as a subtraction, as a difference. And then inside a log, if you have an expression to the power p, the p can be moved as a coefficient. So this is called log property. So let's practice using log properties. We use log property to write like multiple log in an answer into one log. Like, maybe when you do an derivative or when you plug in something, you have a whole bunch of log. you should use log probably to combine them and then write it as one number. So we know ln 125 subtract is the same as 125 divided by 5, right? Then plus ln 1 over 25. After we combine them, we can write it as ln 25 plus ln 1 over 25. When you add something to log, you can combine them as multiplication. 25 times 1 over 25, that is equal to 1, simplify as 1. So that is ln1, and ln1 is 0. So all these add together is actually 0. So the B part is to do the reverse. I have a whole complex expression of x, and I want to write them as individual log. You'll see that we use it to do log differentiation. So I see the top has a x squared x minus 1, but the denominator has cube root of x plus 2. So I'm going to do a subtraction. It will be this, subtract this. ln of x squared x minus 1 subtract ln cube root of x plus 2. And then inside the first one, I see a multiplication of x squared and x minus 1, so I split them as ln x squared plus ln x minus 2, because that's what log property is about. You have two expressions that multiply each other. Inside a log, you can split them into two individual. Minus, I can rewrite this as ln x plus 2. Remember, cube root is power 1/3. Why do I do that? Because whenever I have a power, I can use the log property of moving the power to the front. So it becomes a very simple log of 2 ln x plus ln x minus 2 minus 1/3 ln x plus 2. X plus 2. Can I split it more? I cannot. If you have log, inside log a difference, two terms, you can't split them anymore. So this is the best we can do to write them as individual log, and it is more easy to manage when you do derivative. Okay, so let's talk about redefining log function by itself without depending on the function e of x. So what is a log function? We can use the function y equal to 1 over x to define it. 1 over x is a graph like this. What we can do is, okay, I'm going to define a function as an area from 1 to x. When x is greater than 1, this is my x. From 1, I move my x to whatever place it is. This area from 1 to x is my ln x. I can define it this way. But if x is less than 1, I can define it the same. I would say from x to 1, 1 over t of x is also negative ln x, or I would do from x. So I would say from x over 1 over t d of t dt, because x is less than it. So I would say this is all equal to ln x. So when I switch it back as 1x, 1 over t dt, I would have a negative ln x, right? So you can see 1x can be the whenever I say 1 over x, it can be written as 1 to either x on the left side or x on the right side. And you can also see this definition will allow ln 1 equal to 0 because 1 over t dt is 0. And also ln x is increasing. So it matches whatever that we know about ln x. Secondly, we also look at log properties. If I define ln x this way, using the fundamental theorem of calculus of definite integral, So I would see that ln AB is actually ln A plus ln B, which is the log properties. So it seems like if I define ln x this way, it matches exactly what we have our O ln x as an inverse of e of x before. So the difficult part in this proof, if you're interested looking at why this work is, you can substitute u or t prime equal to a over t. And then if that is the case, then dt prime would equal to or um, oh no, t over a. This would be t over a. I define it as using t prime equal to t over a. Okay, so if that is the case, then a over t would be 1 over t prime, and dt prime would equal to 1 over a dt. Over a dt would become dt prime, 1 over t, and then we also switch all of these to a and 1. So it depends, so it becomes ln a plus ln b. So whatever that we find by defining ln x this way actually match exactly what we have done. So we can still use this integral, or actually by antiderivative, integral of 1 over u du would be ln absolute of u plus c. And because of antiderivative, we can say d, if I do du on both sides, d dx of ln x would equal to 1 over x. So this is what we have before. So when we define log this way, it matches exactly as what we have done before. So it's nothing new. But you can think about ln x as an area function now. Okay, so let's just review all the log. Let's think about all the log. Yeah, let's do some example on ln and there an integral of a function of 1 over x with that would result in ln. Later on in chapter 3, we'll actually do integral of ln, which use other method. So if I want to do the derivative of ln 2x squared plus 1, you would know that this is, assuming this is u, so it will be ln 1 over whatever that you have, which is u 2x squared plus 1, and then time d dx of 2x squared plus 1. So 2x squared plus 1 is 4x. I have it written as the top. And then I have the 2x squared plus 1. So that would be the derivative. So you would see that this is actually the derivative of the denominator, and this is a denominator after you do the derivative of ln of u. So you can see if this is not x, if I have ln u, and you do d dx of, maybe I'll put it here. So the chain rule allows us to say d dx. If I have ln and then instead of x but u, it would be equal to u prime. That means you have the whatever that you have in the top. Oh no, if you do u prime, no, you do u at the denominator because that is 1 over it. And then u prime will be in the numerator. Does that make sense? So like here, I have ln 2x squared plus 1. I'll put 2x squared plus 1 as a denominator, and then do a derivative of 2x squared plus 1 in the numerator. Do the same thing here, but this one is very complex. So we would use log properties. We don't want to deal with these. We would say, okay, I have a exponent inside a log. I will rewrite first. So this is not a derivative. I will rewrite. I'll rewrite it as d dx. I still haven't done the derivative. I'll rewrite it as 3 ln of 2x squared plus 1 x4 minus 2, right? But this is still too complex. I'm going to rewrite it, still rewriting. D dx, still waiting to do d dx of what? 3 times ln 2x squared plus 1, and then minus 3 times ln, because they're dividing, so you subtract x to the 4th minus 2, right? So why do I make it like that? Because I can do the derivative of individually, which is very easy. It becomes 3, I'm doing ln derivative would be the whole thing become in the denominator, right? Anything inside the log is denominator, and I do a derivative, which is 4x. Minus also 3, what is it? This one in the denominator, and then the derivative of it is a numerator, because of chain rule, 4x cubed, right? So you can actually, we need more space here. So at the end of the day, after you simplify it, that is equal to 12x over 2x squared plus 1 minus 12x cubed over x4 minus 2, and we're done. So we don't need to do chain rule, we don't need to do quotient rule, so much faster. The second one, let's do the third one, let's do it. So it is a 1 over ln x. I want to do a derivative of it. So that would be as if I'm doing a dx of ln x to the power negative 1. So this is kind of like a power rule, right? So we would say, okay, I'm going to do the derivative of u to the power negative 1. So the derivative will be negative 1 ln x to the power negative 2 times d dx of ln x. d dx of ln x is 1 over x, and this one is negative 1 of ln x square, right? Because negative 2 is times 1 over x. So it will be negative 1 over x ln x square. That's the answer. The next example is about integral of 1 over 3, 1 over x. So I'll move the 1 over 3 out, and it's 1 over x dx. Whenever I have 1 over x dx, that's ln x, so that means ln absolute x plus 3. What about this? I would need to do substitution, because I can only do 1 over u, right? 1 over u. But this is, I would say u is 3 plus 2 at 2t. So du would equal to t dt. I have a dt here, so du over 2 would equal to dt. And then I'm going to, change the 2 also. U substitute, change it to u also, be 3 plus 2 times 2 equal to 7. About the lower limit, e of 0 would equal to 3 plus 2 times 0 is equal to 3. So this whole thing, maybe I'm going to just do it at the bottom. I would say that would equal to, so this things now change it into 7, 3 dt. dt is du over 2. So that means du over 2. And the front will be d1 over u. Okay, so be 1/2 outside, 7, 3, 1 over u du, Whenever you have 1 over u du, that's ln u. So that would be 1/2 ln u, plug in 7 and 3. So be 1/2 ln 7 minus ln 3. But minus can be written as what? Dividing. 1/2 ln 7 over 3. So in the next video, we'll talk about exponential and some exponential, log differentiation, and also the more difficult, differentiating, more difficult function.